This lesson is for FST, lesson 6.2 on sets with and without overlap. Got a lot to cover today, so we'll try to get to it right away. You are allowed to use baby calculator here. I don't know that you would really need a calculator, but if you need a calculator, feel free to grab a baby. If you have a graphing calculator available, that will be perfectly fine as well. Graphing calculator is not necessary, however. First, we're going to talk about mutually exclusive events. Mutually exclusive is something that you'll hear out and about in your regular life, and possibly if you watch TV, watch the news. Mutually exclusive is a fairly common terminology that you will hear out and about in the real world. For this class, you need to know really well what mutually exclusive means. Real simply, mutually exclusive events do not overlap. They don't intersect. So if you think about it in terms of a Venn diagram, the sets themselves don't actually touch or overlap at all, or if they do overlap, the part where they overlap has nothing in it. So mutually exclusive events don't overlap. You should repeat that to yourself several times. Mutually exclusive events, what? They don't overlap. What that means in terms of real life and probability is that they can't happen at the same time, and the probability of those events is going to be 0. So what we're going to do next is just read through a bunch of examples and non-examples of mutually exclusive. So first example, you go to the basketball game, you go to a hockey game. You can't attend both of those at the same time. You have to go to one or the other. So going to a basketball game and going to the hockey game the same night are mutually exclusive events because none of us can be in two places at once. More mathematical example, you roll an odd number, you roll an even number on a single die on a single roll. We all know that if you have a single die and you're only allowed to roll once, you can only roll an odd or an even. You can't roll a number that's both. I think that's pretty straightforward. Another example here of mutually exclusive events, drawing an ace and drawing a king from a deck of cards from a single draw. When you draw an ace, it's never ever going to be a king at the same time. So you can't draw an ace and a king, so those two events are considered mutually exclusive. Let's look at some non-examples, examples that are not mutually exclusive. The event of going to a hockey game and a different event of wearing a green jersey. Is it possible to do both at the same time? Absolutely. So going to a hockey game and wearing a green jersey are not mutually exclusive because they can occur at the same time. Another non-example is rolling an even number and rolling a 2. If you roll a 2, that's automatically going to be an even number. So those two events overlap, which means they're not mutually exclusive. Drawing an ace and drawing a spade. There is one card in the deck that satisfies both of those at the same time. So drawing an ace and drawing a spade are not mutually exclusive. Hopefully that gives you some understanding now of what mutually exclusive means. Mutually exclusive means they do not overlap. Taking that definition, now we're going to extend it to another topic called complementary events. Complementary events are automatically mutually exclusive, which again means they don't overlap. So complementary events will not overlap, and they have an additional characteristic. The probabilities of the complementary events have to add up to 100%. Usually when you're dealing with complementary events, there's only two events that you're working with. So if one of the events has a probability of 70%, the other one has to have a probability of 30%. The way that we talk about that in symbols is we say the probability of event A plus the probability of event not A has to end up being a 1. If that doesn't make sense to you, let's try it with some practical examples. Let's take our first example of the probability that you will watch TV tonight. The complement to that is the probability that you will not watch TV tonight. So together, those two events can't happen at the same time. Either you will or you won't watch TV, so those are automatically mutually exclusive. And together, those two probabilities have to make a 100%. If the probability that you'll watch TV tonight is 90%, then the probability that you won't has to be 10%. So that's a real life example. Let's do a more mathematical example. What's the probability that you roll a 5 or a 6 on a single die? Well, we know that the probability of rolling a 5 or a 6 is 2 out of 6. There's 2 outcomes out of the 6 possibilities. So the complement to that, in terms of the definition, we would say is the probability of not rolling a 5 or a 6. But let's be more clear about that. A better answer here would be to say the probability that you do roll a what? 1, 2, 3, or 4. And so that we can easily find the probability of has to be 4 out of the 6. So together, rolling a 5 or a 6 and its complement, rolling a 1, 2, 3, or 4, together that covers all the possibilities, and the probabilities together have to add up to 1. Let's do one more mathematical example. Probability of drawing an even card from the deck. The complement to that would be, in terms of the definition, we would say the probability of drawing a non-even card from the deck. But let's make that a little bit more specific. If you don't roll an even, or if you don't draw an even card from the deck, that means the probability that you are drawing an ace, a 3, a 5, a 7, a 9, jack, queen, or king from the deck. And so then again, that would cover all the different possibilities for the probability. So the probability of drawing an even, and the probability of drawing all of those would add up to 100%. Some quick non-examples for you, things that are not complementary. And they may be not complementary for different reasons. We're going to try to list those as we go here. The probability that you'll watch TV tonight, its complement is not that you'll wash your car. Obviously, it is possible for you to watch TV tonight and wash your car, so those are not mutually exclusive. As soon as two events are not mutually exclusive, then they can't be complementary either. You have to be mutually exclusive before you can even be considered to be complementary. So if they overlap in any way, you can automatically say they're not mutually exclusive and therefore they are not complementary either. So this first non-example is not mutually exclusive and not complementary either. Second example, probability that you'll roll a 1 or a 2 and the probability that you'll roll a 5 or a 6. Now these are mutually exclusive. These two events will not overlap. However, the probabilities will not add up to a 100%. There's still another event here that we're missing. Rolling a 1 or a 2, rolling a 5 or a 6, there's still two more possibilities, two more outcomes that we're not talking about here. So even though they are mutually exclusive, they're not complementary because they don't add up to 100%. Final example that we'll talk about here, final non-example, probability that you'll draw a spade or a heart, and the probability that you'll draw an even. And so this one, if you draw a spade or a heart, that's half of the cards. Drawing an even card is not the other half. So obviously there's lots of problems with this non-example. For sure there could be some overlap here. You could draw an even card that's a spade or a heart, and so that's not mutually exclusive. Therefore, it would not be complementary either. Plus, there's all these other cards that have not been accounted for, like drawing a odd-numbered diamond would not be included in this list, and we need to have all the possibilities accounted for. Our other topic for today is the addition counting principle, taken from page 369 in your text. The formula for the addition counting principle, sometimes referred to as ACP, addition counting principle. The formula here looks complicated and scary. I'm going to try to break it down for you so that it's not quite so overwhelming. P is going to be, of course, standing for probability all the way across. And the two events here are just A and B. So we've got the probability of two events, and we're doing the union symbol in between. Remember that the union symbol has a keyword here of the word or. So we're talking about two events, one event or the other happening. So if we're trying to find the probability of A or B, the way that we calculate that is we calculate the probability of A, the probability of B, add those together. But we take away any intersection of the two. So the intersection is the overlap. Keyword there would be and. So we find the probability of A, we find the probability of B, add those together, but we take away any place where probability of A and B overlap each other or intersect. So let's try that now with a couple of examples. Keep in mind that when I memorize this formula, I kind of keep the P on the outside of the whole thing, And I just memorized this. The union is going to be A plus B minus the intersection. So I kind of keep this in my mind, and then I just remember I have to do the probability of all of that. That makes it a little bit easier, a little less messy, and a little less cluttered, and it's much easier for me to remember it that way. So you can give that a try. So let's go ahead and do some practice problems here. Let's consider a pair of dice is thrown. What's the probability of rolling a sum of 7 or, keyword there, a sum of 11? Keep in mind that the dice may or may not be pictured for you, so if the dice aren't there, you might want to actually list out all the outcomes for yourself so that you have it available visually. Since it's already pictured here for us, we're going to go ahead and utilize it. As soon as the presence of the word or shows up and I have two separate events, I'm going to go ahead and just write out the formula for myself. I know that the union of the two events is going to be the probability of A plus the probability of B minus any overlap. So A is going to be the first event that's mentioned, the sum of 7. B is going to be the second one that's mentioned, the sum of 11. So I'm going to just figure out where those are in the picture. Sum of 7, that's going to be what, a 3 and a 4? So I'm going to find that here in the picture. So 3 and 4 is there, and there's got to be another one, 3 and 4 there. Could also do what, 5 and 2, and then 1 and 6. So the probability there is 1, 2, 3, 4, 5, 6 out of, remember how many there are? 36. Now yes, I can reduce that fraction, but let's wait because I'm going to be doing some adding and subtracting. And when you do adding and subtracting of fractions, you want a common denominator. So we'll wait till the end to do any reducing as needed. Now let's do event B, sum of 11. So I'm thinking 5 and 6 here. So 6 and 5, 5 and 6. And there's no other pair that's going to add up to 11, so that's it. So 2 out of 36 is my sum of 11. Now the intersection would be anything that I've circled for both sets. I didn't circle anything in red and purple, so what does that mean? Think about our vocab from today. These two events are mutually exclusive because there is no overlap for us to take away. The formula still says to look for it though, so we're just going to say we're not going to take away any because there isn't any. And so our union here is just going to be the two sums added together. Or excuse me, the two probabilities added together. So 6 plus 2 there is going to be the 8 out of the 36, and then we simply reduce that fraction to lowest terms. So we can divide everything by a 4 here. 8 divided by 4 is 2. 36 divided by 4 is 9. So let's try that one more time with a slightly different question. What is the probability that the dice show doubles or a sum of 7? Again, with the presence of the word or, I know that I'm going to be doing A plus B minus the overlap. That will get me the or, which is the union symbol. So let's do doubles as event A, sum over 7 as event B. So doubles, let's find where those are in the picture. There we go, and it looks like there are 6 of those. And then let's find event B, which is a sum over 7. So 7 is not included here. So I'm going to find where my 7s were, and I'm going to find everything bigger than that. So that ends up being, here's a 7, here's a 7, here's a 7. Everything below that is going to be higher than 7. So all the purple ones there are the ones that are going to count. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I wouldn't have known that without the picture. So it's really important that you have the list of the sample space in front of you so that you can count how many outcomes that would be. It's really the only way you can figure that out is by visually counting it out. Now let's look for where the overlap is. Overlap would be things that are circled in blue and purple at the same time. So the only ones that that qualifies for are the blue ones that are inside the purple region. So that looks like 3. So there were 3 that were in the overlap, 3 that were in both sets, doubles that are bigger than 7. So 4 and 4, 5 and 5, 6 and 6, those all add up to numbers higher than 7, so those are the 3 in the overlap. So now let's go ahead and add. 6 plus 15 is going to be 21 minus 3 is going to be what? 17? No, 18 out of 36. So we end up reducing that down to a half.